So, we will continue our band theory of solids. So, we have seen this how band is formed. So, energy versus wave vector relation is very important, as I mentioned. So, what we have seen this, that there is a break in this EK curve. That curve was so this kind of this break is there. So, these are first billiardian, then second billiardian, third billiardian. So, each this represent a basically band, and this is the band gap, and then another band, second band, second billiardian. Now, in this band, this first band, first billiardian, in this band, so we have energy levels, right? We have energy levels for, so how many energy levels means there is a corresponding wave functions will be there. So, or k state will be there. So, how many states or wave function or orbitals are present in a band. So, that we have calculated in last class. So, number of wave function in a band if this crystal have a finite length, if the crystal have a finite length, if crystal have a finite length of L. So, in this L length there are n number of lattice point which are separated by distance a, periodic lattice, one dimensional periodic lattice, total length is L, okay, total length is L. So, total number of primitive unit cell having a one lattice point, that is called primitive unit cell. So, how many cells will be there? So, that will be L equal to, so each cell length is A. So, if n number is cells, so N A. Okay. So, A is basically L by N, and then so it has finite length L. So, it has to satisfy this wave function, whatever wave function, number of wave function we want to find out. So, this wave function has to satisfy the boundary condition psi x plus L, whatever here. So, it is generally take is a ring boundary condition. If you just enclosed it, so this here whatever value here it has to be same value. Okay. So, this psi x. So, the Bloch function, this wave function for periodic potential, this Bloch function. So, this u k x plus L e to the power I k I k plus x, sorry. So, e to the power I k x. So, here x plus L x plus L equal to u k x e to the power I k x, right. So, from here you can, from this condition you can get I k L has to be 1. So, 1 means e to the power I 2 pi n, okay, n equal to plus minus 1, plus minus 2, plus minus 3. So, e to the power I 2 pi, 4 pi, 6 pi, plus minus. So, it will be 1. Okay. So, from here this k L equal to 2 pi n. So, you are getting k equal to 2 pi n by L, right, 2 pi n by L. Okay. So, k, so for wave function in a periodic potential, this it can take k value, this plus minus 2 pi by L plus minus 2 pi by 4 pi by L, right. So, what will be its upper limit? So, it can take infinite number of value. In principle, it can take infinite number of value, but in this Billigen, first Billigen, so how many states are there? So, what is the upper limit of this k value? Okay. So, in that case, this k is so in Billigen k equal to plus minus pi by a. So, that is the boundary. So, that is the maximum value of k. Okay. So, this a, if we put a equal to L by n, so we will get plus minus pi n by L, plus minus pi n by L, right. So, you can see plus minus pi n by L. So, this is the maximum number of, that is the maximum value. Okay. So, in first Billigen, that is the maximum number of value. So, in first Billigen, so this k value plus minus 2 pi by L plus minus 4 pi by L, so it can take maximum value pi n by L. It can take maximum value pi n by L. Okay. So, this basically this number is so here k, it can take maximum how many? It can take maximum n by 2, right. So, 2 pi n by 2 by L, I think that is the so this is plus minus this k value we can take plus minus 2 pi by L, plus minus 4 pi by L. So, it can take, so this number basically n by 2, 2 pi into n by 2 by L. So, this will be n by 2 number, total term will be n by 2. So, plus minus are there, total n number of k value you will get, total n number of k value you will get, right, and corresponding n wave function, n number of wave functions you will get, okay, and corresponding you will get energy states or energy, or it is called orbitals. You will get n number of orbitals in a fast Brillouin or in a band. In any band you will get the number of states, number of orbitals or number of wave functions that will be equal to the number of primitive unit cell in the crystal of size say L. Okay. So, now here, so that part I discussed earlier. So, important conclusion is so number of wave functions in a band is n, right, which is the number of primitive unit cell in the finite crystal. Okay. So, you have band, right. So, this is one band, so I think, so we have first Brillouin, second Brillouin, third Brillouin. So, in each Brillouin you will get as a energy band. Now, how many energy levels will be there? So, if one primitive unit cell in that finite crystal, one primitive unit cell. So, in each band, you will get one line. In each band you will get one line. Right. So, this for first Brillouin, second Brillouin, third Brillouin, etc. There are many bands. Okay. Now, if you increase the number of primitive unit cell one by one, so then for 2 number of primitive cell in each band 2 energy level. If you increase one more, so you will get 3, you will get 3, you will get 3, right. So, similarly 4, 5, 6, 4, 5, 6, 4, 5, 6. Okay. So, that is why this band formed. Okay. So, so number of electrons in each band, how many number of electrons one can put. So, that is so electron spin up and spin down. Okay. So, in each energy level, in each orbitals 2 number of electrons can be put. Okay. So, if you take a material, which is made of a atom, and that atom has one valence electron, one valence electron, right. So, n number of primitive unit cell, n number of atoms will be there. So, n number of electron, free electron will be there, valence electron, free electron will be there. Okay. So, this first Brillouin there, this first band, it will be half filled, because it can take 2n number of electrons, but our total number of electrons is n. So, it will be half filled. Okay. It will be half filled. Okay. Now, if if two valence electrons are there, if two valence electrons are there per atom, then what will happen? Then 2n number of electrons, so it will be full filled. So, half filled, right. Now, it is full filled, right. Now, it is full filled. Okay. So, other way also, if atom is having one valence electron, but two atoms basis as a basis, two atoms in one primitive unit cell, it is not lattice, one lattice per unit primitive cell, but lattice have a two basis, two atoms. Okay. So, then also two valence electron per unit cell. Okay. So, you will get 2n number of, so in that case also it is fulfilled. Okay. Now, this when it is half filled, so these electrons have, so all other energy levels are very close. So, these electrons can move freely. Okay. So, then this type of solid is show the behavior like metal. When it is fulfilled, so then that electron, it cannot go anywhere, right. To go to the only levels are available in the next band, but there is a gap, energy gap. So, it has to overcome. So, it is not free. So, you will not get free electron. So, in that case, it is either semiconductor or insulator. It is insulator. Now, in case of semiconductor, at temperature T equal to 0, so this it behaves like it behaves like insulator. Okay. But at finite temperature, say at room temperature, so it can behave like it will have some free electron, and it will behave between insulator and metal. So, when it is fulfilled, so it is insulator or semiconductor. So, when it will be insulator, when this band gap, Eg is quite high. So, then it will be insulator. If this band gap Eg is quite small, then it will behave as a semiconductor. Okay. So, in case of semiconductor, in case of insulator, so these are basically its full fill band. Okay. Now, to get free electron, electron has to move in another band, and that is only possible if band gap is small, comparable to the room temperature or slightly higher than room temperature. Then it will behave like a semiconductor. Okay. So, semiconductor at room temperature, at absolute temperature T equal to 0, it is basically insulator. Okay. So, so that is what you see this our when we studied this free electron theory, when we studied free electron theory, quantum theory, this is quantum theory. So, then it was able to explain most of the properties of metal, right, but it was not able to answer. Why some materials are metal, why some metals are insulator and some metals are semiconductor. So, that answer could not be found from this free electron theory. So, that is why this band structure band theory of solids are required. And finally, I showed you that this theory can answer why some solids are metal, some are insulator and semiconductor. How one can distinguish these solids in three category based on their electrical conductivity. Okay. So, including this theory, it can explain this whatever from free electron theory, whatever we got. So, in general this band theory, it can explain this all materials, solids. So, either it is metal or either it is semiconductor or either it is insulator. Okay. So, this is a quite general and successful theory. And so, now, so in a band, what we got in a band, how many number of orbitals are there, states are there, wave numbers are there, that we got, fine. Now, when electron in a band, what is its velocity? Whether its velocity is same as the velocity of free electron or it is different. So, that we want to find out. So, velocity when electron in a band, what is its velocity? So, basically this plane wave, travel wave. So, this it is generally we write e to the power I k x minus omega t, right. That is the wave function for free electron. So, this is basically phase, this is basically phase k x minus omega t, it is called phase and this is called amplitude, right. Now, here k dx, so if I differentiate, so this is equal to phase, this constant, okay. This is a phase, this is a constant. So, when a wave is moving, okay, it's so we consider that this wave are moving. So, this its phase are moving, that phase. So, it is moving such a way, it has to move such a way that its this phase remain constant. So, so we are finding out the velocity of a wave, means velocity of a particular phase, how it is moving with time, right. So, we have to consider that particular phase. So, that is why we are considering this, that phase is constant. Okay. So, differentiate it k dx minus omega dt equal to 0. So, dx by dt is omega by k. Okay. So, this is called phase velocity, Okay. But, so this free electron, it has velocity. So, that is called phase velocity, but when electron in a lattice, so basically it is not phase velocity, we tell it is a group velocity, So, group velocity is defined as group velocity So, this is the phase velocity we write, say Vp, okay, equal to omega by k, but phase velocity group velocity it is defined as a Vg equal to d omega by dk. Okay. What is that? When this there is a dispersion, when this not only a particular k omega, okay, if there is a so there are many components close to that, it is within this d omega and dk range. So, it is basically k is not unique k is k plus delta k and omega is omega plus delta omega. Okay. Then you will not get simple just plane wave, you know, it is not like this, it is not like this. So, this wave, when there is a dispersion, there is a range of omega and k. Okay. So, then it is you basically I think so, it is going on. Okay. Okay. So, this type of wave packet, this is form wave packet and wave packet are moving, okay, with velocity, with group velocity. Okay. So, here you can see two periodicity, one is this as a whole, this is moving. So, this one periodicity is this. Okay. So, this is basically phase velocity, these are moving with a velocity, that is phase velocity. Another as a whole, this surface of this one. So, these have also periodicity, these have also periodicity, as if these are moving, these are moving. Okay. This envelope is moving. Okay. So, wave as a whole is moving, wave packet is moving, wave packet is moving. Okay. So, this velocity is called group velocity. Okay. So, this basically this that individual, this is omega by k, this phase velocity, but this wave are moving with this velocity, the envelope moving. So, that is group velocity. So, in this case wave packet are moving. So, that is velocity is group velocity, but there also this phase velocity, that main component, that is also it is moving with the packet. So, that is Vp with this velocity, it is moving. Okay. So, that is the group velocity. So, when electron in the band, so it will no longer it is a free electron, no longer it is a free electron. So, it will move with not phase velocity, it will move with group velocity. So, Vg equal to d omega by dk. So, this g I will remove. So, just V equal to d omega by dk. Okay. So, what we know about this energy, because E k relation is very important, as I told. So, this is known to us, if known to us. So, E equal to k h cross or h cross k, right. So, dk by d by dk equal to h cross, right, dE by dk equal to h cross. So, sorry, so this is the momentum h cross k equal to h cross omega, sorry. So, I can so omega is a function of k and E is a function of k. So, I can differentiate d E by dk equal to h cross d omega by dk. Okay. So, d omega by dk equal to 1 by h cross dE by dk. Okay. So, this is the group velocity. So, if you know the energy k value relation, then you can find out the velocity. Okay. So, here just if I consider the first Billiardian, so here this first Billiardian is known to us. So, this is the E k relation, right. So, this is E and this is k. So, okay. So, here you see this d by dk is nothing but slope of this curve, dk is nothing but the slope of this curve. So, here the slope is 0 and then slope is positive, then here you see this is one curvature and then this is another curvature. Okay. This is one curvature and this is another curvature. Okay. This curvature change at this point. So, this called what is called inflection point, where curvature change, this is called inflection point. Okay. So, if you draw corresponding velocity, what will get? So, here velocity is 0 because this is 0 and here also flat velocity is 0. So, you will get here velocity 0, here velocity. So, in between you will get maxima, okay, and other side its opposite is negative. So, you will get okay. So, this at inflation point, basically this is the inflation point. So, my drawing is not correct, basically I should draw like this, okay. So, at inflation point it has to be maxima, velocity is maximum. So, at inflection point velocity is maximum, say this is V0 and others velocity is 0, right. This is important relation, important findings. Now, here you see the electron in a crystal in a band. Now, its velocity at the bottom of the band it is 0, at the top of the band it is 0, but in the middle of the band it is maximum, right. So, if you apply electric field, okay, so then electron will move with some velocity, with some acceleration, right. But you see its velocity is different in the upper top than the lower bottom. Okay. So, these are very important findings. So, that is the velocity, that is one, find out the velocity from this E k relation. Okay. So, thank you. I will continue in next class.